radiotoxicity. Bottom line is it's considerably lower in a lifter than it is in a pressurized water reactor or a light water reactor. The fission products are the same in both cases, but notice how much quicker it takes you to get to what we call the background, the natural level of radioactivity that you have in uranium ore. And in about 300 years, you're all done with that. Another way to look at this, next slide. I think once at a time. In a current light water reactor, you start with 250 tons of uranium. This is for a 1 gigawatt reactor, 1 gigawatt power plant operating for 1 year. You need 250 tons of uranium, and then you have to enrich it to 35 tons of enriched uranium. Basically, most of this is U-238. A small percentage is uranium-235, less than 1%. And you want to kick that up to about 3.5%. So that's the enrichment process. All you're doing is you're taking a particular type of uranium and separating them, trying to put more on one side versus the other. And of that 35, you put it in a reactor, stays there for about a year. A lot of it is burned, consumed, if you will. Some plutonium-239 is produced and burned. And then you wind up with, well, you put 35 tons in per year, you wind up with 35 tons of spent fuel coming out. Most of that's just uranium-238. It's no more radioactive than it started with. But you also produce some transuranics, that 0.3 ton of plutonium, sort of the nasty stuff that everybody worries about. And you could reuse that as fuel, but we elect not to do that in our current scheme of things. The French have been working on ways to do that, to actually reprocess the fuel, pull out the plutonium, and consume it. Yeah, go back up, go back. So, in a thorium reactor, you can start with 1 ton of thorium, and basically you would consume all of it, turning into 1 ton of fission products. Now, those will be radioactive, but in about 10 years, a lot of that will be stable. And because you're using this in a liquid form, you can extract those fission products, and those will be, some of those have a market value. You can sell them. Other part of it is a lot of that has value in the medical field. There's a lot of medical procedures and diagnostic procedures that require radioactive elements. And where do you get those? Right now, there's 2 research reactors in the world that produce almost all of them. Here you can produce them as just a byproduct of your power generation. So you can use those things and become cheaper since you're producing a lot more. You do produce some plutonium, but you're talking about 0.0001 tons or about 100 grams of the stuff versus 0.3 tons in a standard reactor. So another advantage of these designs is they're much lower capital costs. For the next slide. Here's a basic schematic of a standard water reactor power plant today. The business end of it is taking place in here. That's your reactor core. Now in the reactors, you're generating a lot of heat, and it's kept cool by water in the reactor. The water burns at, or excuse me, water boils at 100 degrees centigrade, 212 Fahrenheit. That's not hot enough to be efficient in terms of energy production or electricity production. You want it to boil at about 300 degrees C to really drive a steam turbine system. So how do you make it boil at a much higher temperature? You keep it under pressure, like a pressure cooker. Well, what you're left with is a design where your reactor core is in water, under pressure at about 2,000 psi, or 140 atmospheres. And if anything goes wrong, pipe were to break or something, all that water at that temperature in that contained structure is let loose. Flashes to steam. That steam that got out of there would fill up this building. And that's the reason why that building is the size that it is, so that if this event happens, all that steam is contained. The other thing is, water keeps the core cool. If water flashes to steam, it doesn't remove heat as efficiently as water. So now you're worried about the solid fuel melting down and releasing the fission products. So your cores, your solid fuel is your first containment in these designs, and they always worry about a meltdown where you release them. And if you release them and they come out outside the reactor core itself, they go into this building. So this building has to be very big. It's made out of reinforced concrete. And then you have all these systems around to pump water on that core if things go wrong. If you lose some of the pressure, we got a pump for that. If you lose a lot of the pressure, we got a different pump for that. Always trying to figure out how to keep that core cool. Well, so if you take a step back and say, well, what do we have? We have a fairly large, that's about 5 meters across, a fairly large pressure vessel running at 2,000 psi that's made out of very thick steel, and that that has to be fabricated to nuclear regulations. It's got to be rather big. You have a big building here made out of reinforced concrete, and you have all these systems to put backup water on this thing. This all drives the whole design of the building. Is this event? The building is expensive, you have a lot of equipment, and then you have all these nuclear regulatory things you have to maintain and meet for safety, reliability, and all these other things. That's what drives the cost of these things. It's really the safety inherent in the basic nature of it, plus the fact that you have your core under pressure with water that can go to steam. You contrast that with a lifter. You have fluid form at atmospheric pressure. There's no pressure vessel here. That's a huge advantage. And there's nothing that can flash the steam. So you don't need a steel containment vessel. You don't need a concrete building around it. You don't need pumping systems to deal with cooling it in the emergency situation. If you have a problem, you just drain it to a tank where it's passively cooled. And then, of course, there's a lower recurring cost. There's no fuel fabrication in something like this. It's just a liquid. You just dissolve it, your thorium, and make your thorium tetrafluoride, and dissolve it into the salt, and away you go. Here's a look at a typical set of uranium pellets in a light water reactor. You see each of these pellets are about maybe a ½ inch or so in diameter. They're manufactured to very exacting tolerances. They have a zirconium cladding around a uranium oxide core. You see the guy holding it with the glove on his hand, and you might be inclined to think, that's there to protect him from that uranium, which is radioactive. That protects the guy. That would be wrong. The glove is there to protect the uranium pellets from him, not the other way around. You don't want to get any of your body oils or sweat on these things because they're manufactured at very exacting tolerances, and they go into these tube systems that fill up your core. So these things need to be clean. So to keep them clean, every time somebody handles them, they have to wear these gloves. It's really not an issue of protecting himself from the fuel, it's protecting the fuel from him. And then, of course, one of the biggest advantages that you get with the thorium fuel is you're probably looking at an impossible situation in terms of running out of fuel. At 12 parts per million of thorium in the ground, it doesn't sound like a lot, 12 parts per million. But recall that the energy density is over 1 million times greater than any fossil fuel. So now you have a 12-fold greater energy density in dirt than you have in a barrel of oil, a ton of coal, amount of natural gas, anything like that. So it kind of changes the thinking. What we're talking about is roughly 10 times more energy in dirt everywhere on planet Earth versus going digging for something specific like coal or oil or natural gas. Because you're talking 12 parts per million, which is the average in the Earth's crust. So if you think about it, you're talking about dirt having 10 times the energy that oil does. I would submit to you that you probably will never run out because you've got an entire planet's worth of fuel. And if by some crazy means we did run out, there's also thorium on the moon, there's also thorium on the asteroids and other planets. And that may sound crazy, who's going to mine the moon? Well, if you have this kind of energy capability at a million-fold density, interplanetary space travel suddenly isn't as daunting as a task because you have a power source, which is usually the biggest problem with spacecraft, that enables you to move through the solar system with much greater ease. You can have bigger, heavier rockets, and you can manufacture them in space. So things like going to other places in space, which this is out there thinking, admittedly, but this enables that type of stuff a lot more so than we're currently capable of. So why the liquid fluoride thorium reactors? Why that particular design? I mean, you could do nuclear power a million different ways. There's just a ton of ways to design a power plant, design a nuclear reactor in a core. What's so advantageous of a lifter? Well, for one, they have been proved at Oak Ridge for about 4 years. And so this is not a paper theoretical thing. A lot of this work is actually done. Here's a look at the reactor at Oak Ridge back in the day. Here's the reactor core in its hot cell. And that was a small reactor. It was about 7.5 megawatts of thermal energy coming out of it. But it was, appreciable in size, and they can work out all the science that they needed to get that all ironed out. And for a couple of years, it actually ran at full power at different fuels. They actually ran U-235 in it, they ran U-233 in it, at full power for over a year. Another issue that keeps showing up in the world of nuclear is proliferation. Everyone's afraid that the nuclear material, which is fissile, which you can make a bomb out of, is going to be somehow stolen, taken away. That's far, far more difficult to do than you might think. First of all, that stuff in a power plant is highly radioactive. If a person goes to try to steal it, he's probably going to die. Second thing is, even if he did steal it, it's almost inevitably contaminated with uranium-232, which is a hard gamma emitter, which makes it really easy to spot, really easy to detect. And if you build a bomb out of that, you run into trouble in that gamma emitter messes up all your electronics for making weapons. Bottom line is, there are no nuclear weapons, no operational nuclear weapons ever built using uranium-233. They looked at it in the early days of the Manhattan Project and they just said, this isn't going to work, and they left it aside. There was one, in 1955, they did a test called Operation Teapot, where they actually attempted to use a U-233 core in a bomb, and it basically fizzled. It detonated, but it generated about half the energy they thought it was going to, and they're not sure why. So there was no other attempt to use 233. No government in the world uses uranium-233 to build weapons out of it. And frankly, if you really wanted to build a weapon, the easier way to do it would be just to enrich uranium-235 right out of natural uranium ore. Now, the higher temperatures that you enable here, if you use a light water reactor, you boil water, maybe 300 degrees C is all the hotter it gets in the core. Here you're using a liquid fluoride, which is stable up to about 1500 C. It stays a liquid, it holds all the fission products in. It's got a very large range of where it's a liquid. Using the higher temperatures enables you to do other things, like generate synthetic fuels and different fertilizers. It's kind of a look at what you might do. You can use the nuclear heat to drive the process where you take water and you basically break it down into hydrogen and oxygen. And with the hydrogen, you can construct other materials or other fuels. Dimethyl ether could go right into a diesel engine today. Methanol could be a replacement for gasoline for cars. And ammonia is used today a lot in fertilizers for agriculture. About 1% of the world's energy production goes to fertilizers or ammonia production. And it's currently starts with natural gas is the most common way to do it. But with a high temperature nuclear reactor, you can generate all these materials, all these substances right from the heat of that. So you can use the heat to do anything that currently requires energy in other forms today. And then because they're relatively simple to build, it's just a pot, it's not a pressure vessel, and you need a pump to pump it to a heat exchanger and some piping. That's really the heart of it. It's 3 simple parts. Now you would have some computer control stuff and make it behave nicely if you wanted to, but in general, the heart of the thing is pretty simple. And so you can build these things small, and you can build them in a factory in a mass-produced kind of way, and that will keep the cost down. And typically, as you produce things in the factory over time, you actually take more and more costs out of it as you kind of learn processes that are more efficient. And common design helps keep that going too. Here's kind of a look at what they do at Boeing. And we use Boeing as a model because Boeing has some similar issues. For example, they produce something on the order of 1 aircraft a day at about a $200 million cost per aircraft. We can see that being a lifter plant being a similar type of production activity. There they have such things as safety issues. You have the same set of safety issues you're concerned about here. There you got a lot of materials issues. You've got the same thing here. You have materials issues. I think at the end of the day, building an airplane is probably more complex than building liquid power plants. But we've already done the more complex thing in a factory. We can build another factory to build lifters. It's kind of modeled off of the way Boeing does things. So, what are our challenges with lifters? Why hasn't this happened? What's making this tough to do? Well, it's a different design, and basically our NRC, Nuclear Regulatory Commission, just in a nutshell, they don't understand the architecture and all that. It's too new for them. The technology never really left Oak Ridge all that much. It largely resided there. It never really germinated to other national labs, and the commercial industry never really left the light water reactor technology. Now, you can go to the NRC and say, I would like to get a license, and they'll look at you funny and say, okay, give us several $1 million a year, and we will study it, and we'll get back to you in about 10 years. So that's not really much of an opportunity for a business startup model. And we like the startup model for something like this because it does represent a very disruptive technology. And my background comes from a technology company, and the startup model allows a small company to compete and even eventually supplant a larger company if they can generate something that's new enough and it brings a different dimension of value to the overall marketplace. As this is very promising in doing that. So our biggest problem is how do we cut through the red tape? How do we get the NRC to enable us to license these things in a simple fashion? How can we make this a much more streamlined process? That's one of the biggest issues that stops investors from going into this. Bill Gates has funded to the tune of $40 million in TerraPower, which is a nuclear power startup company. Different architecture, different paradigm than liquid fluoride thorium reactors, but it is a modular reactor design he's funding. But a lot of the people that fund this are more far-thinking, far-reaching in their mindset. You can't really expect to get a return on your investment in the typical 3 years, 5 years that a lot of venture capitalists like to see. It's not that they're not out there that are willing to go further, but the opportunities to get funding drop off rapidly. So we believe that if we can eliminate that red tape, streamline that process, we will see a lot of private money willing to go into something like this. So, bottom line, thorium could represent energy for the planet in excess of what we're consuming now forever. We think that the liquid fluoride thorium reactor represents the architecture of a nuclear reactor that achieves that. It uses it most efficiently and it really enables true energy independence. If you want to learn some more, there's a three websites you can click on. There's a bunch of information and data on thorium reactors, lifters, and a lot more that I can go into today. So, and it concludes my talk. Yeah, it hasn't really taken off. This has been sitting around since the late 60s. So what's up? Well, like I said, Oak Ridge kind of kept the technology sort of close to the vest, which probably did not suit them well, because when it came time, you remember Nixon had this energy independence by the end of the decade. Then every politician since him said, energy independence by the end of the decade. Nixon actually had a plan to achieve that. The only politician that actually had a plan. The plan didn't work out, but he actually had a plan. And his plan was to use breeder reactors to achieve that. Now, he wasn't a nuclear engineer or a nuclear technologist by any stretch, but he was going on a competing technology to the thorium uranium cycle. He was big on breeder reactors using uranium plutonium. And the reason why that was more advocated back then is it was in the middle of the Cold War. The scientists and engineers understood plutonium. They were making bombs out of it. They knew the metallurgy, they knew the physics of it. It was something that they were familiar with. So going that path made more sense to them. Thorium uranium, pretty much, for a lot of these guys, was just new, and it would have been starting over. Weinberg was always pushing this. He thought this was far safer than the uranium plutonium breeder reactor. He thought this is definitely the way to go. But he was making a big stink, and the powers that be in Washington basically fired him from his position on head his own international lab. And since then, the technology is just kind of stagnated. Nothing's really happened with it. The funding that this got was never anywhere near the same level of funding as the fast breeder reactor, or the liquid metal fast breeder reactor, that the uranium plutonium cycle was. At this point today, I look at it and I say this should work. Why doesn't it work? And I think the biggest hurdle is the regulatory environment is just killing it. Nobody wants to invest in it if they don't see any way to get a return on their investment. And you can put money into all the R&D you want, but you can't license a reactor. So how do you turn it into a money stream? I think one of our biggest problems is getting over that hurdle, is getting legislation in place so that licensing can happen. Once that happens, I think you'll see a lot of venture capital coming. There's been a lot of advances in the last 40 years or so in material science to what you want to build these out of, things like that. And there's a lot of research going on in this, and a lot of the research in maybe the last 10 years or so is really starting to pick up. But in terms of actually turning it into a product, it just hasn't gotten there yet. From my perspective, the biggest hurdle is the environmental part.
When was the last new nuclear reactor put online? Right along.
It was like 90s, the last one was actually put online. Can't remember the name of it, but there was, and it got licensed, I think, in the late 70s, but it just took quite a while to put it together.
How costly is it to extract from dirt? And can this be made in a small package plant, like for a run big company or a city or something?
You could make it in a plant, probably something similar of what Boeing does. Depends on what type of manufacturing speed you want to do, how many units per day, for example. Getting your first question, how difficult is it to get the thorium out of dirt? It would be a process, but again, you're talking about an energy density that's so much greater than what we have now. For example, when they smelt iron ore, you take effectively dirt out of the ground, or if you take the dirt that's very high in iron concentration, you effectively melt it, and then you take off the iron and you drive off the oxygen to that pure iron. And the rule of thumb there is it takes about a ton of coal to melt a ton of iron ore. Well, here we got roughly 10 times more energy to begin with, so even if it takes a ton to a ton, you're still only using roughly 10% of the energy to get it out. And that's if you get it out of the crust of the air. And really, the problem's not even that far. There's a lot of places a lot of mines today that generate a lot of thorium as a byproduct. You might have heard Obama talking several months ago about rare earth elements and how China's cornering the market and being unfair. Well, in this country, we have more rare earth elements than we need. Rare earth elements aren't that rare. We have pretty much all of it. So why don't we mine it? Primarily, we don't mine it because whenever they mine for rare earths, they always pull up thorium. And they don't like it because thorium is radioactive. Very low level of radioactivity. You can put it under your pillow and go sleep with it, it won't hurt you. But it is radioactive. So according to our current regulations, you must treat it as low level nuclear waste. Well, the miners look at this and say, I got to incur this huge cost associated with my mining operation of how to deal with thorium, which is almost always there. So all the rare earth element mines in the U.S. are the ones that have the minimum amount of thorium for the amount of rare earth elements that they can find. They're always looking for the ones that are thorium poor. And there's a lot of thorium-rich ones, and they don't want to touch them. So there's a lot of this stuff that gets pulled up just by the natural operations of rare earth mining. There's a guy, Jim Kennedy, and you can find him on some of his talks on the website. He has a rare earth mine. He pulls up about can pull up about 5,000 tons of thorium per year. 5,000 tons would just about power the world. So, there you go. And then the U.S. government, at one time in the early, I guess it was in the 50s, 40s or 50s, they were stockpiling thorium, thinking that this was a strategic material to have. They couldn't figure out what to do with it, so they buried it in the desert under 12 feet of dirt. There's 3,200 tons in the desert under 12 feet of dirt. Just the way that you can use it. So, you know, there's a lot of places on Earth where thorium is far more concentrated than 12 parts per million, and that's where you would start. But if you want to go really long thinking, you can get it out of 12 parts per million. It's economically viable to pull it out of good old-fashioned dirt anywhere. So there's really no monopoly on it or anything like that. You would start with all the places you already have it, all the low-hanging fruit, but maybe a few thousand years from now, people would have to maybe get it out of the ground in a little more complex way. I would argue this is a renewable resource simply because even though it is consumable, there really is no way you can run out of it. And for that matter, geothermal is consumed. It's not renewable forever. Solar, not renewable forever. The sun's only got about 4 billion years left in it, and then it's going to go out. So you probably don't have to sweat anything, but if you want to be technical about it, if you get long enough out there, it is exhausted. So with that sort of overall view, I would say that thorium really represents a renewable resource.
So how much is China spending a year to go forward with this technology?
Yeah, China started a project not long ago to develop this technology. They are something like a 400-man research and development team going on over there. And they're getting a lot of assistance from our government to develop molten salt reactor technology, molten salt thermodynamics, things like that. So just thought I'd throw that out there. It's pretty pathetic. I don't understand it. Why we would do these things, but why not invest here to make this happen here? Yes?
How do we help you give voice to this?
Well, one of the things I've been doing is starting an organization called energyfromthorium.org, which we're trying to get that out into the people's understanding of this technology. We're trying to start more of a grassroots effort so that we're not there yet. We just got kicked off not too long ago. We want to get a 501c3 going and then have it possible for people to make donations online to do that. But our goal is to affect some legislation and to get a lot of educational stuff out there so that more and more people know about it, which is also why I'm here today. Any other questions?
Was there any way to start one in a state and experimentally and bypass all the federal regulations?
Within a state, I think it's different. One of the problems with the state is a state has, to kick one of these off, you have to start with some fissile material. By law,
How about the state with the 3,200?
they don't have, that's not fissile material, that's fertile material.
Oh,
Thorium itself is not a fissile material. You need a sort of like a kickoff charge of fissile material. You could use uranium-235 or plutonium, or uranium-233. Oak Ridge has quite a bit of it. It's at Oak Ridge is still there. By law, all fissile material is owned by the federal government.